Linear regression. Use a regression equation to make a prediction. Compute the residual for a prediction. Lesson objective. Here is an example of a regression line. This is computed by StatCrunch, and this is the two variables, shoe size and height. These variables were from the MAT 131 student survey. And here we see roughly a linear pattern, and StatCrunch can plot the line of best fit along with the scatter plot. If you recall, the regression equation is y equals b plus mx. This is how StatCrunch outputs the values. The first value is the y-intercept, and the second value is the slope, and that is always multiplying your independent variable. So here's the StatCrunch output for shoe size versus height. The dependent variable is height, the independent variable is shoe size. So we would use this linear model to take a shoe size to predict the height. The third line is the regression equation, and if we round this off to 2 decimal places, the equation becomes height equals 51.88 plus 1.63 times shoe size. The 51.88 is the y-intercept, and the 1.63 is the value of the slope. If we were to interpret the value of the slope, we could use our template. As the x variable increases by 1 unit measured by the x's, the y variable is either going to increase if the slope's positive or decrease if the slope is negative. By how much? Well, that's the value of the slope, m, and the units will be what's measured in the y. And technically we could add on average, which means that in statistics, if there are multiple values for a certain x variable, the value of the y would be the average of those. So in the terms of our problem, we would say as the shoe size increases by 1 size, that's the units for shoe size is the size, the height increases by 1.63 inches because inches are the units for the height. And then we can add on average. As the shoe size goes up by 1, on average the height increases, gets larger by 1.63 inches. Let's look at the y-intercept. Here's the template for the y-intercept. It is a point. It is the predicted value of the y when the x is 0. Now many times the y-intercept does not make sense in the terms of the problem. And usually that's because the value of x may not make sense in the problem. But there's times where the value of x does make sense, or there's data near the value when x is equal to 0, and then it could make sense in the terms of the problem. So for our example, when the shoe size is 0, the predicted height is 51.88 inches. That's the interpretation of the y-intercept in this situation. But we should say that this really doesn't make sense in the terms of the problem because we don't have any data near a shoe size of 0. And can a Cincinnati State student taking MAT 131 have a shoe size of 0? No, but that's okay. That is the interpretation of the y-intercept. The y-intercept is needed as an initial value for this regression equation, but that point in itself doesn't make sense in the terms of this problem. Nobody has a shoe size of 0. Now let's use this equation to make a prediction. If the shoe size is 12, what is the predicted height? Round it to 2 decimal places. So we take our equation and we substitute 12 in for the shoe size, and we follow the order of operation. We have to multiply before we add, and we add these two, and that is our prediction. So a shoe size of 12, this model is predicting a height of 71.44 inches. Now it is unlikely that the exact height for one student with a shoe size of 12 is exactly 71.44, but it should be close. How close? Well, we need to talk about what is the residual for that person, which brings up our next lesson objective. Compute the residual for prediction. What is the residual for a 131 student who has a shoe size of 11 and a height of 72 inches? In order to compute the residual, we need to know three things. Number one, what is the value of the independent variable? Number two, what is the value for the dependent variable? And number three, what is the predicted value of the dependent variable using the value of the independent? So for this example, the shoe size of 11 is the value of our independent variable. This student has a height of 72 inches. That is the actual value of the dependent variable. Now we need to compute what is the predicted height for a student having a shoe size of 11. We do this exactly like we did in the previous example. We take our regression equation and we're going to use a shoe size of 11 to get the predicted height. So if you substitute an 11 into that equation, you should get 69.81 inches. The residual is the observed height minus the predicted height. Recall, the observed height or the actual height for this student is 72 inches. The model is predicting 69.81 inches. So it's close, but it's not exact. The residual is always the observed minus the predicted. It's alphabetical order. O comes before P. So it's the observed minus the predicted. For this example, it's 72 minus 69.81, which is a positive 2.19 inches. Let's go back and look at our StatCrunch output. Here is the output from StatCrunch. If we look down where it says parameter estimates, notice the first one says intercept and the second one says slope. There will be certain situations where you're given a software output and this is what you see. Now, can you make the equation from these values? And the answer is yes. This intercept is telling us that is the value of the y-intercept. The slope is the slope of the line. So we just need to combine these two into an equation and we have our regression line. So we have y equals 51.53 plus 1.68 times x. And in this case, y is the height and x is the shoe size. Now you may notice that these values are a little bit different than the previous example, and that's because this is using data from a different semester. So when you use the student survey data set to compute the line of best fit for height and shoe size, these numbers will be close, but they're probably going to be a little bit different. Let's do another example. Here is a software output and we're asked to find what is the equation of the regression line. So if you can just remember, intercept means your y-intercept and this is the value of the slope. So for this example, the regression equation would be, we always start with our y, our dependent variable, and that is equal to a negative 10,534.2 plus, because our slope's positive, and this is 60.245 times x. Given the information that we have here, this is involving baseball, but we don't actually know what is the independent variable and what's the dependent variable. And for this example, that is okay. I just want you to be able to look at an output and then determine what is the y-intercept and what is the slope. Let's do another example. Here are two more variables from the student survey. The independent variable is distance, and that question asks how far do you live away from Cincinnati State, and the units are miles. The dependent variable is commute time, and commute time asked how long does it take you to get to Cincinnati State, and that was measured in minutes. So we would use this model to take a distance to predict commute time. So this roughly looks like a linear pattern. There are a few little outliers here, but overall it looks pretty good. And again, in statistics, we would want to look at the value of the correlation, and we'd want to look at the value of R squared, which is the coefficient of determination. And that would tell us how strong of a linear relationship this is. Let's look at the output from StatCrunch. If we look at the parameter estimates, the y-intercept is 11.88 rounded. The slope is 0.85 rounded. So to 2 decimal places, this is our equation. But we can also, of course, have the equation here. And I actually like this equation better because we clearly define what our variables are. Dependent variable is commute time, and our independent variable is distance. Let's interpret the slope. So we would say as the x variable increases by 1, as the distance increases by 1 mile, the y variable, in this case the commute time, would increase because the slope is positive by 0.83 minutes on average. So for each additional mile away from the college, your commute time is going to increase 0.83, a little bit less than a minute on average. The y-intercept can be interpreted this way: when the distance is 0 miles, the predicted commute time is 11.88 minutes. This is reasonable because if we go back and we look at the scatter plot, we do see some data near 0. And in the terms of this situation, if we think about it, there could be students who live less than a mile away from the college, but they have to walk to school. So it is going to take them a little bit of time, even though less than a mile away from the college is not a big distance. It does take a little bit of time to walk to school. This is a reasonable interpretation for this situation. To use this equation to make a prediction, what is the commute time for a student who lives 20 miles away from the college, rounded to the nearest 10? We're given that distance is 20 miles, so we take our equation, we substitute 20 in for distance, we multiply the slope by 20, and then we add the y-intercept, and we get a commute time of 28.48, and if we round it to the nearest tenth, this turns out to be 28.5 minutes. So a student who lives 20 miles away, this model is predicting a commute time of 28.5 minutes. Thanks for watching.